Hello everyone. I will speak about testing TDI on experimental data on the LISA on-table experiment. I'm Léon Vidal. I'm a third-year PhD student at APC in the Gravitational group. So as you might know, LISA will detect gravitational wave in the millihertz band. And to do so, we will measure the distance fluctuation between distant free-falling test masses performing laser interferometry. So with arms about 2.5 million kilometers, we expect a distance fluctuation between these free-falling test masses around the picometer. And for LISA laser in the infrared, we expect phase fluctuation of this laser due to the gravitational wave around the microradian. So to perform measurement between free-falling test masses, we have what we call split interferometry. It consists on performing three kinds of measurements. The first one is the science signal to measure the distance fluctuation between two distant optical benches. Then we have the test mass signal to measure the fluctuation between one adjacent optical bench in the same spacecraft and one local test mass. And at the end, we have the reference signal, which measure the fluctuations between one adjacent optical bench and one local optical bench in the same spacecraft. At the end, we can reconstruct the signal interferometric measurement with these three measurements to get a test mass to test mass fluctuation. So we have a lot of different noises in LISA, but I will focus on the laser frequency noise because it's the dominant one due to the LISA architecture. In fact, it's due to the laser instability in frequency, but LISA, it's an unequal arm interferometer, so this laser noise will be dominant in the LISA data. And if we do nothing, even with the best space qualified laser, we will have 8 order of magnitude of this noise above the gravitational wave signal. To reduce this noise, we have what we call TDI for time delay interferometry. So you may know what TDI is, but here is the basic idea behind TDI. We have one noisy sources, laser source, and we measure this noise in two different places. First time on the local optical bench and second time on the distant optical bench. So it's the same measurement, but with the distant optical bench, which is delayed. And so the idea is to delay the local optical measurement here, and then we can get a noise-free combination around these two, between these two delayed data stream, and we can reduce or cancel directly the laser frequency noise of our data stream. So for the real LISA TDI algorithm, it's a little bit more complex, but the idea is the same, is to combine different signals, science signals, test mass, and reference signals to remove the optical bench and the test mass displacement to get just a test mass to test mass displacement. And then we will delay this, what we call TDI variables, to get a combination. So here, it's a noise-free combination called the Michelson combination. And after some computation, we can show that it only remains a gravitational signal. So to produce a realistic LISA data, we have different simulators, which are software simulators. But at APC, we have also the LISA on table, which is an instrumental electronical simulator of LISA, and for a simplified constellation. So we can describe this experiment in three different parts. The first part is the control command part, which allows us to choose the simulation parameters and to generate radio frequency signals. Then these signals will be mixed together to produce bit notes in the electronical interferometer. So we have delayed and not delayed radio frequency signals to produce realistic bit notes. And at the end, we have the phase meter, which will measure this phase fluctuation of our signals. And then it will filter and downsample this data to send it at a lower rate to the computer, and then we can apply TDI directly in the computer. But the step of filtering and downsampling is really important for the rest of this presentation, and I will show you how. So here's a little picture of the electronical interferometer of LISA on table. And so the inputs of this interferometer is, as I said, delayed or not radio frequency signals. And the output is two different TDI variables for the two arms of LISA on table. So the first result we had for TDI1 was a little bit weird because when I chose two fixed arms for unequal arms, so yeah, LISA on table is just classical Michelson. We don't have three arms like in LISA. And so I choose different arms, size of arms, and I do the trip around LISA on table and then apply TDI on the data. And we saw this curve. So the blue one is the TDI, the raw TDI variable on the channel 1 of the phase meter. The black curve is the intrinsic noise of the experiment, which is just the sensitivity of LISA on table. And the green one is the residue after applying TDI to our data, TDI1. So at lower frequency, we can see that we have 8 order of magnitude of noise reduction, which is what we expect. But at higher frequency, we have increasing residue. So at first, we didn't get what was this effect. And so we wanted to try if when I apply a delay with TDI in Python or with the lot LISA on table, do we apply the same delay? So to do so, we made up this little toy model. So we have here a laser noise, which is just a white noise computed with the LISA on table. And on one branch, I delay this laser noise with LISA on table. And then I measure it with the phase meter. On the other branch, we directly measure the laser noise without delays, without LISA on table delays. And then I apply a delay with Python, like a TDI delay. And I see the result of this operation. Do we have a residue at the end? And the result is here. So in blue, we have the raw laser noise. In black, the sensitivity curve of this setup. And in blue, we have the residue. And we can see that we have the same increasing at high frequency. And we did some simulation to explain this curve without with bias or ranging noise when we apply TDI, but no simulation can explain this shape. And then we dig a little bit more in the phase meter measurement. So we have what we call CIC filters in the phase meter with sampling process, which is just downsampling. And the goal of these CIC filters is to avoid aliasing in the LISA bandwidth, but also to downsamplate our data at lower rates for the downlink in LISA. And we made the assumption that this CIC is aliasing some noise also. And here's the formula of the residue of this operation if we take into account the aliasing of this CIC. And we can see that this operation is not commutative at all, because in one case we filter and then we delayed, and in the other we delayed and then we filtered. And so we have here this formula for the residue depending on the CIC transfer function here and the sampling period, the output sampling period of our CIC fs here. So we plotted this formula and we can see that we have a match in red between our analytical formula and with the blue one, which is the experimental residue. And so we did the same computation for TDI1 applied on LISA on table data. So we get this big formula here. And if I plot this formula, we have a really good match. So it's the red one here, analytical formula, which matches really well with the green residue. of TDI, experimental residue. And so we did the same for TDI2. And so we can explain this weird curve with CIC aliasing. So in LISA, we have also CIC in the phase meters, but we don't have the same sampling period and output sampling period. So maybe we have aliasing, but not at the same frequency. And maybe it's a problem, maybe it's not a problem in the LISA band. So we wanted to make sure about this. And so we did a little simulation. So for the LISA decimation schematics, we have two different CIC at two different decimation factors, going from 10 megahertz to 640 hertz. And then at the end, we have three different finite impulse response filters. And so here I plotted the trend of the aliasing terms for each of my two CIC. So here's the first CIC going from 80 megahertz to 10 megahertz, and we can see that the aliasing is not entering in the LISA bandwidth. Here in magenta, we have the LISA phase meter requirement at 1 picometer. But for the second CIC filter, the aliasing, we have two curves here for two different orders of this filter. And when the order is lower than 3, so just 2, we have aliasing in the LISA bandwidth. So this is just the aliasing and not the coupling with TDI, as I showed you just in the other slides. But the incoming works will be to have an analytical formulation for the coupling of this effect for LISA in the case of TDI1 and TDI2, and then study the non-stationary noises for the flexing arm in LISA case. Thank you. If you have questions, you can send me an email.